Thin lenses and ray tracings. First, we're going to talk about converging lenses. And converging lenses are lenses that are thicker in the center. If I was to draw a converging lens, I need a principal axis. And then I have a vertical line, which represents the lens. The shape of the lens, which is a converging lens, looks something like so. And then we have a focal point. So we'll put a little point here and write F prime on this side. And on the other side, we'll put a point and write F. Now the distance from F or F prime to the vertical line is known as our focal length. If I have an object to the left of my focal point, then we can draw some rays to show where the image will form. Our first ray comes off of the object. When it strikes the lens, the ray of light refracts and goes through the focal point. So this is ray number 1. The next ray actually goes through the focal point. When it strikes the lens, the ray refracts and moves horizontal. This is ray number 2. Ray number 3, this is my favorite one. This one starts off the object and goes through the center of the lens, like so. And this is ray number 3. Where all 3 rays intersect, that's where your image will form. So my image in green will be right there. As you can see, my image is inverted. And my image in this case is real because light rays are passing through it. Okay, now we're going to talk about diverging lenses. Diverging lenses are thinner at the center. So for drawing a diverging lens, we have our principal axis. We have our vertical line, which represents the lens. The shape of the lens is thinner at the center, like so. We have our focal point, F on this side. It's the right side where we have F prime in this case. If our object were to the left of the focal point, we can do our ray diagrams or ray tracings. Ray number 1 comes off horizontal, and when the ray reflects, it actually let's try that again. It refracts upward, and it's as if the back tracing would go through the focal point, like so. So that's ray 1. Ray 2 actually wants to go through the F prime. So the ray heads towards the F prime. When the light hits the lens, the light refracts horizontally, like so. So that's ray 2. But if the ray were to continue, it would go through the F prime, like so. And I'm actually interested in the back tracing of the refracted ray in step 2, and that goes back like so. A back tracing of the horizontal line. Hopefully you can see where I have the blue dotted line and the black dotted line where they're crossing to find out the formation of the image. But we can do our third ray if we want. You don't have to do a third ray to find the formation of the image, but we could do it just in case to see. We're going to go off of the object through the center of the lens. This is ray 3. And so where we have a blue dotted line, a black dotted line, and the red line intersect, that's where the image is. So the image is small. It's hard to see there in green, but that's where the image forms. The image is on the same side of the object, so the image in this case is virtual. It is upright, the size is reduced, but it is virtual. Now I want to talk about the lens equation and magnification for lenses, and it's very much the same as we learned for mirrors. The lens equation looks the same. It's 1 over the distance of our image plus 1 over the distance of our object, and that's equal to 1 over the focal length. And the magnification, m, is also the same. It's the height of the image divided by the height of the object, or what I say, hi-ho, and that's equal to a negative distance of the image over distance of the object, or negative di-do. So now I want to talk with you about the sign conventions when we are dealing with lenses. So I want to talk to you about when things are positive or when are they negative. So if we're talking about a focal length, the focal length will be positive if we're dealing with a converging lens, and it will be negative if we're dealing with a diverging lens. I just want to draw the shape of those. The next item is the distance of the object. If it's the side of the lens where light is coming from, typically the left side, the distance of the object will be positive. If the object is on the right side of the lens, or where the light is not coming from, then it will be negative. The next thing is the distance of the image. If it is on the right side of the lens, it will be positive, and it will be real. If the image is on the left side of the lens, or the same side as the object, or where the light is coming from, the distance of the image will be negative in value, and it will be virtual. The height of the image, if it's upright, it's positive, just like with mirrors. If it's negative, it's inverted. The height of the object, we're going to say, is always positive. And for magnification, if your object is upright, we'll have a positive value for magnification. If it's inverted, we will have a negative value for magnification. So just putting in the lines for a table here. So you should memorize these when we are dealing with lenses. Okay, let's do an example. In this example, we have a lens. The distance of the object from the lens is 10 centimeters, or it's on the left side of the lens. It's positive because it's where the light is coming from. And we have a focal length of a positive 15 centimeters. Because the focal length is a positive 15 centimeters, we know then we are dealing with a converging lens. So drawing a diagram of our converging lens, we have our lens here, and we have a focal point, or what I'd call F prime on this side, an F on this side of 15 centimeters on both sides. And my distance of my object is between the focal point and the lens. So my object is somewhere here. There's my object. So in this problem, what is the distance of the image and what is the magnification or the size of the image? So the formula we're going to use is the lens equation, which is 1 over d sub I plus 1 over d sub O is equal to 1 over the focal length. Or we can say 1 over d sub I is 1 over the focal length minus 1 over d sub O. So plugging in numbers, 1 over d sub I will be 1 over 15 minus 1 over 10, and that gives me an answer negative 1 over 30. So take the inverse of both sides, and the distance of the image is equal to a negative 30 centimeters. The negative means that the image is going to form on the left side of the mirror, and that means that the image is virtual. The magnification, which is going to be negative di over do, will be a negative times a negative 30 over the distance of the object, which was 10. And we're going to get a positive answer of 3. So my image is going to be 3 times as tall as the object. If we go back up to my original diagram, we can draw a ray tracing to see if this is truly what we see. So going back up, let's draw our ray tracings. My first one goes here. It's ray 1. The next ray I want to draw, I really only need 2 rays, and wherever they intersect, that's where my image is going to form. So I'm going to go from the top of the object through the center of the lens. And when I draw this ray, I see on the right side of the lens, these are never going to cross. So I need some back tracings here. The red one goes back like so, and the back tracing for the black ray goes back like so, and we have a crossing over here. So my image actually forms to the left of my object. There's my image. As you can see, it is on the left side. It is bigger than my object, so the ray tracings validate what the equations show. Okay, so the last thing I want to talk about is combination of lenses. So what if you have more than one lens? So you have your principal axis, and let's say we have 2 convex lenses here. We have some object starting over here, our focal point. We'll call this lens A, and we'll call this lens B. So this is some focal point for lens A. And this side will have FA. And then here, let's say we have our focal point for lens B. And we have it on the other side here, F sub B. And what we have here, let's get a different color, but we have, this is the distance of object A is in green. Here we have the distance. Well, we don't know that one yet. Hang on. Okay, so here's our drawing of our 2 lenses, and let's see what else we are given. So what we have given here is the focal length for lens A is 20 centimeters. The focal length for lens B is 25 centimeters. Notice that these focal length values are both positive, so this would also indicate converging lenses. Lens A and lens B are 80 centimeters apart. And the distance of object A is a positive 60 centimeters or 60 centimeters to the left of lens A. And so in this problem, we want to find the distance of the image from lens B, and what is the size of the image B, or what is the magnification of the image from lens B. So in order to solve this problem, we want to find out where is the image forming from lens A, and let's do some ray tracings to show this before we use some formulas. And so first thing I'm going to do is go to my object to the left of lens A and see if I can find where the image forms just from lens A. So I'm drawing my first ray here, what I call ray 1. And I'm just going to use, I think, the third ray, which goes through the center of the lens. I only need 2 rays where they intersect. This is what I usually call ray 3. And then I get my image here, approximately there. And we're going to call that the image from lens A. And what I have here then is the distance of the image for lens A is this distance here. Now what I'm going to do is take the image from A and make that my object for B. And notice my distance for what I'm calling the object for B is this distance here. And we'll be finding that when we use the equation. If I want to go ahead though and draw my ray tracings, I have, if I look at image sub A, which is also what I'm calling the object for lens B, I have a horizontal line that comes off, which then refracts through the focal point like so. So that's my ray 1. And then in red, I'm just going to go through the center of the mirror like so, and they will cross somewhere here. So my image is right there. So this is my image that forms from lens B. Also, I have a distance here, distance of my image B, which is from there to there. So I'm going to use the lens equation, which is 1 over DIA plus 1 over distance of the object A is equal to 1 over the focal length A. And from there, I can find the DIA, which is 30 centimeters. And once I have that, and I know that the total distance between the two lenses this is given is 80 centimeters. If this is 80 centimeters and my DIA is 30 centimeters, then my DOB is going to be 50 centimeters. Now once I know my distance of the object from lens B, which is 50 centimeters, now I can use the lens equation again and find, in this case, DIB plus 1 over DOB, which is 50 centimeters, is 1 over F sub B. So my DIB, by plugging in the numbers, also ends up being 50 centimeters. And lastly, then, we're going to find the magnification. Again, magnification is negative DIB over DOB, which in this case is going to be a negative 50 centimeters over 50 centimeters, or we get a negative 1.00. So according to this, the size is the same, the magnification being 1. Negative meaning my image for B is in the opposite direction as my object for B. So let's just go back up to the drawing and notice that my image for B, which is right here, is inverted. And let me say that again. My object for lens B is inverted, and my image for lens B on the right side is upright. So they are in opposite orientation to each other, which indicates that negative for the magnification. Okay, time for practice. Okay, so this is pages 660 to 661 out of your textbook, numbers 47 and 61. Good luck.